Hello, and welcome to the Cozy Curiosity channel. Tonight, we turn our gaze toward the restless mountains of fire, places where the Earth's molten heart breaks through stone and speaks in smoke and ash and rivers of light. Volcanoes are both creators and destroyers, building new land even as they reshape what already exists. They rise from the planet's deepest layers, carrying stories written in heat and pressure, in crystals formed far below the crust. To witness a volcano is to glimpse the forces that have shaped every continent, every ocean floor, every breath of atmosphere that surrounds us. Tonight, we will wander through that fiery world, tracing how volcanoes form, how they erupt, and how they touch every corner of life on Earth. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. But for now, just breathe. Allow your eyes to grow heavy and let the glow of distant peaks warm your thoughts. Let's begin. Volcanoes form where Earth's tectonic plates meet or separate. Deep beneath the surface, the planet is divided into massive plates of solid rock that float atop a layer of molten stone. These plates drift slowly, colliding at some boundaries and pulling apart at others. Where they meet, one plate often slides beneath another, sinking into the hot mantle where it begins to melt. The molten rock, lighter than the surrounding stone, rises through cracks and chambers until it finds release at the surface. Where plates pull apart, magma wells up from below to fill the gap, creating new crust and often forming volcanic ridges that stretch for thousands of miles beneath the ocean. Each volcano marks a place where the Earth's interior reaches toward the sky, where hidden heat becomes visible fire. The distribution of volcanoes around the world is not random, but follows these plate boundaries with remarkable precision, sketching an outline of the planet's restless foundation in peaks of smoke and stone. The Ring of Fire contains about 75% of the world's active volcanoes. Circling the Pacific Ocean like a horseshoe of flame, the Ring of Fire is home to roughly 3/4 of Earth's active volcanoes. This vast arc stretches from New Zealand through the Philippines and Japan, across to Alaska, and down the western coasts of North and South America. The ring forms where the Pacific Plate collides with surrounding continental plates, creating conditions perfect for volcanic activity. As oceanic crust sinks beneath lighter continental rock, it melts and rises, fueling eruptions that have shaped the landscape for millions of years. The region is also marked by frequent earthquakes, a reminder that the same forces driving volcanic activity also shape the ground. Communities living within the Ring of Fire have learned to coexist with this volatility, building cultures and mythologies around mountains that breathe smoke. The ring is a testament to the power of plate tectonics, a visible scar where the planet's surface constantly renews itself through fire and motion. Magma becomes lava once it reaches the Earth's surface. The distinction between magma and lava is simple but profound. Both are molten rock, but magma exists beneath the ground, while lava flows above it. When pressure builds within a volcano's magma chamber, the molten stone forces its way upward through cracks and vents. The moment it breaks through to open air or water, its name changes. This transformation is not merely linguistic but physical. Underground, magma contains dissolved gases trapped by the weight of overlying rock. At the surface, those gases escape violently, driving explosive eruptions or bubbling quietly from flowing streams of lava. The temperature of both can exceed 2100 degrees Celsius, hot enough to melt steel or vaporize water instantly. Yet lava, exposed to air, begins cooling immediately, forming a solid crust even as molten rock continues to flow beneath. This dance between heat and cooling, between hidden and revealed, defines the life of volcanic rock, from its birth deep in the mantle to its final rest as solidified stone. There are more than 500 potentially active volcanoes on land. Across the continent, over 1,500 volcanoes stand ready to erupt, though not all are currently active. These peaks represent a spectrum of behavior, from those that erupt frequently to others that have slept for thousands of years but retain the potential to awaken. Geologists monitor these volcanoes carefully, watching for signs of stirring, small earthquakes, rising ground, changes in gas emissions. The definition of potentially active includes any volcano that has erupted within the past 10,000 years, a blink of an eye in geological terms. Some, like Mount Etna in Italy, erupt almost continuously, offering regular displays of lava and ash. Others, like Mount Rainier in Washington, appear peaceful but harbor magma chambers that could fuel catastrophic eruptions. The global network of volcanoes reminds us that the Earth's interior is alive with motion, that what seems solid beneath our feet is merely a thin skin over a restless, molten heart. The largest volcanic eruption in recorded history was Mount Tambora in 1815. On the island of Sumbawa in Indonesia, Mount Tambora exploded with a violence that reshaped global climate. The eruption killed tens of thousands directly through pyroclastic flows and tsunamis, but its influence spread far beyond the island. So much ash and sulfur dioxide entered the atmosphere that it veiled the sun, causing 1816 to be known as the year without a summer. Crops failed across Europe and North America. Snow fell in June. Famine and disease followed the cold. The eruption ejected more than 160 cubic kilometers of material, leaving a caldera 6 kilometers wide where the mountain's peak once stood. Even today, the crater holds a deep blue lake, serene and still, giving no hint of the fury that created it. Tambora reminds us that a single volcano can alter the course of history, affecting weather patterns, harvests, and human societies thousands of miles away. The eruption column reached heights of more than 40 kilometers, punching through the troposphere and scattering debris that would circle the globe for years. Volcanic ash is not actually ash, but tiny fragments of rock and glass. When we speak of volcanic ash, we conjure images of soft grey powder, like the residue from a campfire. But volcanic ash is far more abrasive and dangerous. It consists of pulverized rock, minerals, and volcanic glass, shattered into particles finer than sand during explosive eruptions. Each grain is jagged and sharp, capable of scratching glass, damaging engines, and irritating lungs. When mixed with water, it forms a heavy, cement-like sludge that can collapse roofs and bury landscapes. Ash clouds can travel hundreds of miles from their source, carried by high-altitude winds to blanket regions far from the erupting volcano. Aircraft avoid ash clouds because the particles can melt inside jet engines, causing them to fail. Despite its dangers, volcanic ash is also a gift. Over time, it weathers into extraordinarily fertile soil, rich in minerals that support lush vegetation. Some of the world's most productive farmlands, from the slopes of Mount Vesuvius to the fields of Java, owe their richness to centuries of ash deposition, a reminder that destruction and creation often walk hand in hand. Lava can flow at speeds up to 60 kilometers per hour. The speed of a lava flow depends on its composition, temperature, and the slope it travels. Thin, runny basaltic lava, low in silica content, can race down steep volcanic flanks at speeds approaching 60 kilometers per hour, faster than most people can run. Such flows, though terrifying, are often predictable and rarely cause loss of life because they can be seen and avoided. Thicker, more viscous lava moves much more slowly, creeping forward at a pace measured in meters per hour or even per day. This slow advance allows time for evacuation, but also creates a different kind of destruction, as the lava bulldozes everything in its path, incinerating forests and burying towns beneath layers of cooling rock. The surface of a lava flow often solidifies quickly, forming a crust that insulates the molten river beneath, allowing it to travel great distances without cooling completely. When lava reaches the ocean, it creates new land, extending coastlines and building islands grain by grain, a process both ancient and ongoing in places like Hawaii and Iceland. Some volcanoes erupt underwater, creating new islands. Beneath the ocean's surface, countless volcanoes erupt unseen, their fire quenched by the immense pressure and cold of deep water. Yet when these submarine volcanoes grow tall enough, they break through the waves, birthing new islands in dramatic displays of steam and ash. Surtsey, which emerged off the coast of Iceland in 1963, is one such island. Over several years, eruptions built a landmass from nothing, a new fragment of Earth rising from the seafloor. Scientists watched as life colonized the barren rock, birds bringing seeds, waves depositing driftwood, moss and lichen taking root in cracks. The process of island formation continues today in places like the Pacific, where underwater volcanoes along the Hawaiian chain and other hotspots slowly rise toward the light. Each new island is a laboratory for understanding how life begins on raw stone, how ecosystems develop from emptiness. Some islands grow and endure, while others erode back into the sea. Their brief existence a reminder of the ocean's power to both create and destroy. The word volcano comes from Vulcan, the Roman god of fire. Ancient Romans observed Mount Etna and other fiery peaks with a mixture of awe and fear, attributing their violent outbursts to Vulcan, the god of fire and forge. They imagined him working beneath the mountains, hammering out weapons and armor for the gods, with smoke and flame escaping through volcanic vents. The name stuck, evolving into the word we use today. This mythological connection reflects humanity's long history of seeking explanations for volcanic phenomena, weaving them into stories and beliefs. Many cultures around the world have similar myths. In Hawaii, the goddess Pele is said to reside in the Kilauea volcano, her moods reflected in the mountain's activity. In Japan, Mount Fuji has been revered as sacred for centuries, a dwelling place for spirits. These stories remind us that volcanoes have always been more than geological features. They are symbols of power, transformation, and the mysterious forces that shape our world, forces that ancient peoples personified in gods and spirits, long before science offered different explanations. Volcanoes can create lightning during eruptions. In the chaos of a volcanic eruption, a phenomenon called volcanic lightning can occur, painting the ash cloud with brilliant forks of electricity. This happens when ash particles, rock fragments, and ice crystals collide within the eruption column, generating static charges. When the charge separation becomes great enough, Lightning arcs between particles or from the cloud to the ground, illuminating the plume in spectacular displays. Photographs of volcanic lightning show jagged bolts threading through dark ash clouds, a fusion of fire and storm that seems almost otherworldly. The exact mechanisms are still being studied, but the process is similar to how thunderstorms generate lightning, only in a much more violent and turbulent environment. Volcanic lightning can occur in eruptions of all sizes, from small explosive bursts to massive caldera-forming events. Witnessing such an event is rare and dangerous, a reminder of the raw power concentrated in these natural phenomena, where earth and sky collide in bursts of electric fury. Pyroclastic flows are the deadliest volcanic hazard. Among all the dangers a volcano presents, pyroclastic flows are the most lethal. These are avalanches of superheated gas, ash and rock that race down volcanic slopes at speeds exceeding 100 kilometers per hour, incinerating everything in their path. With temperatures that can reach 700 degrees Celsius or higher, they vaporize wood, melt metal, and leave behind landscapes stripped to bare rock. The flow travels as a ground-hugging cloud, heavier than air, filling valleys and following terrain with deadly efficiency. Escape is nearly impossible once a flow is underway. The eruption of Mount Vesuvius in 79 AD produced pyroclastic flows that buried the Roman cities of Pompeii and Herculaneum, preserving them in ash for centuries. More recently, Mount Pelée in Martinique killed nearly 30,000 people in 1902, when a pyroclastic flow swept through the city of Saint-Pierre in minutes. Survivors described a wall of fire descending the mountain, followed by darkness and heat that ended almost as quickly as it began. These flows remind us that proximity to an erupting volcano is not measured in distance alone, but in the speed and direction of its most violent exhalations. Shield volcanoes have gentle slopes and are built from fluid lava. Not all volcanoes are steep, cone-shaped peaks. Shield volcanoes, named for their broad, gently sloping profiles resembling a warrior's shield laid flat, are built from countless eruptions of fluid basaltic lava. Each eruption adds a thin layer, and over time, these layers accumulate into massive structures. Mauna Loa in Hawaii is the world's largest shield volcano, rising more than 4 kilometers above sea level, but its true height, measured from its base on the ocean floor, exceeds 10 kilometers, making it taller than Mount Everest. Shield volcanoes tend to erupt frequently, but less explosively than their steeper counterparts, producing lava flows that spread across vast areas. These eruptions can last for weeks, months, or even years, slowly expanding the volcano's footprint. The gentle slopes allow lava to travel great distances before cooling, creating broad plateaus and wide lava fields. Despite their size, shield volcanoes often erupt without much warning, a reminder that even the most placid-looking peaks harbor molten chambers beneath their flanks, ready to spill forth whenever pressure builds beyond the rock's ability to contain it. Stratovolcanoes are steep and prone to explosive eruptions. In contrast to shield volcanoes, stratovolcanoes are steep-sided, symmetrical cones built from alternating layers of lava, ash, and volcanic debris. These are the classic volcanoes of popular imagination. Peaks like Mount Fuji, Mount Rainier, and Mount St. Helens. Their steep profiles result from thicker, more viscous lava that doesn't flow far before solidifying, combined with explosive eruptions that pile ash and rock around the central vent. The magma feeding stratovolcanoes is often rich in silica, making it sticky and prone to trapping gases. When pressure builds, eruptions can be catastrophic, blowing away entire mountainsides and sending ash columns tens of kilometers into the sky. The layered structure of these volcanoes creates internal weaknesses, and over time, water and ice can infiltrate cracks, further destabilizing the edifice. Some stratovolcanoes are topped by glaciers, beautiful but dangerous, as eruptions can melt ice rapidly, triggering devastating floods and mudflows called lahars. The combination of beauty, symmetry, and explosive potential makes stratovolcanoes both revered and feared, symbols of nature's power to create and annihilate in equal measure. Cinder cone volcanoes are the smallest and simplest type. Cinder cones are the modest members of the volcanic family, typically no more than a few hundred meters tall. They form from a single vent where gas-charged lava is ejected into the air, breaking into fragments that cool and fall back around the opening. These fragments, called cinders or scoria, pile up in steep-sided cones with a bowl-shaped crater at the summit. Cinder cones often appear in volcanic fields, where dozens or even hundreds of small cones dot the landscape, each marking a brief episode of eruption. Sunset Crater in Arizona is one such cone, formed just over 900 years ago in an eruption that lasted only a few years. Because cinder cones are built quickly from loose, unconsolidated material, they erode relatively fast, their slopes furrowing and softening over centuries. Many serve as parasitic vents on the flanks of larger volcanoes, releasing pressure from the main magma chamber. Despite their small size, cinder cones can produce impressive lava flows and local hazards. They are windows into volcanic processes at their simplest, stripped of the complexity that defines larger, longer-lived peaks. Calderas form when a volcano's summit collapses after an eruption. Some of the most dramatic volcanic features are not peaks but vast depressions called calderas. These form when a massive eruption empties a magma chamber beneath a volcano, leaving the overlying rock unsupported. The summit collapses into the void, creating a basin that can span tens of kilometers. Crater Lake in Oregon occupies a caldera formed about 7,700 years ago when Mount Mazama erupted and collapsed. The resulting depression filled with rainwater and snowmelt, creating a lake of remarkable depth and clarity. Calderas can be sites of resurgent volcanism, with new magma rising into the collapsed area, sometimes forming islands or domes within the larger basin. The Yellowstone caldera in Wyoming is one of the world's largest and most closely monitored, a supervolcano that has erupted catastrophically in the past and may do so again in the distant future. Calderas remind us that volcanoes are not static. They grow, erupt, collapse, and sometimes rebuild, cycling through phases over hundreds of thousands of years, each stage leaving its mark on the landscape. Mount Vesuvius famously buried Pompeii and Herculaneum in 79 AD. On a summer day in the year 79, Mount Vesuvius awakened after centuries of quiet, unleashing an eruption that would become one of history's most famous volcanic disasters. The Roman cities of Pompeii and Herculaneum, nestled at the volcano's base, were thriving centers of commerce and culture. When Vesuvius erupted, it sent a column of ash and pumice high into the sky, then produced deadly pyroclastic flows that swept down the slopes. Pompeii was buried under several meters of ash, while Herculaneum was entombed in superheated mud and pyroclastic material. Thousands died, some trying to flee, others seeking shelter in their homes. Remarkably, the ash preserved the cities in extraordinary detail, capturing buildings, artifacts, even the forms of victims frozen in their final moments. Excavations beginning in the 18th century have revealed daily life in the Roman Empire with stunning clarity, from frescoes and mosaics to loaves of bread carbonized in ovens. Vesuvius remains active, and millions of people now live in its shadow, aware of the risk but drawn by fertile soils and the beauty of the Bay of Naples. Volcanic eruptions can cool the planet's climate for years. When a volcano erupts with great force, it injects not only ash, but also sulfur dioxide gas high into the stratosphere. There, the sulfur combines with water vapor to form tiny droplets of sulfuric acid, creating a haze that reflects sunlight back into space. This can cool the Earth's surface by a degree or more, a small change with significant consequences. The eruption of Mount Pinatubo in 1991, for example, lowered global temperatures by about 0.5 degrees Celsius for several years, disrupting weather patterns and agricultural cycles worldwide. The effect is temporary, lasting only until the aerosols settle out of the atmosphere, but it demonstrates the interconnectedness of Earth's systems. Large eruptions in the past, such as Tambora and Krakatoa, had similar effects, altering seasons and contributing to crop failures and famines. In a world increasingly concerned with climate change, these events remind us that natural forces can still rival or exceed human impacts on the atmosphere, at least temporarily. They also offer a sobering glimpse of how fragile our climate balance can be. Geothermal energy harnesses heat from volcanic regions. In areas where magma lies close to the surface, the Earth's heat can be captured and converted into clean, renewable energy. Geothermal power plants tap into underground reservoirs of steam and hot water, using the heat to drive turbines and generate electricity. Iceland, sitting atop the mid-Atlantic ridge, derives much of its power and heating from geothermal sources, transforming a volcanic activity into a national asset. Geothermal energy is reliable and continuous, unlike solar or wind power, making it an attractive option for baseload electricity. The same heat that powers eruptions also warms homes, heats greenhouses, and even powers industrial processes. In some places, hot springs and geysers provide natural bathing areas, drawing tourists and offering therapeutic benefits. Yet geothermal development must be managed carefully. Over-extraction can deplete reservoirs, and drilling into unstable volcanic systems carries risks. Still, as the world seeks alternatives to fossil fuels, volcanic regions offer a glimpse of how Earth's internal heat, normally destructive, can be transformed into a force for human prosperity and environmental sustainability. Hotspots create volcanoes in the middle of tectonic plates. Most volcanoes form along plate boundaries, but some rise in the centers of plates, far from any edge or collision zone. These anomalies are caused by hotspots, plumes of exceptionally hot mantle rock rising from deep within the Earth. As a tectonic plate drifts over a stationary hotspot, magma punches through the crust, creating a volcano. Over time, the plate's movement carries the volcano away from the hotspot, and a new volcano forms in its place. This process creates chains of islands, each progressively older as you move away from the active hotspot. The Hawaiian Islands are the classic example, with the Big Island currently over the hotspot and still growing, while older islands to the northwest are extinct and slowly eroding. Yellowstone is another hotspot, though it lies beneath a continent rather than an ocean. Hotspots reveal that Earth's mantle is not uniform, but contains columns of rising heat, fixed in place, while the crust slides over them like a conveyor belt, leaving trails of volcanoes to mark the plate's journey. The Pacific plate's movement creates the Hawaiian island chain. The Hawaiian Islands are a geological timeline written in stone and coral. Each island a chapter in the Pacific Plate's slow drift northwest. The Big Island, with its active volcanoes Kilauea and Mauna Loa, sits directly over the Hawaiian hotspot. As magma rises and erupts, it adds new land to the island. To the northwest, Maui, Oahu, and Kauai grow progressively older and more eroded, their volcanoes extinct, their peaks worn down by rain and time. Beyond the main islands, the chain continues as the northwestern Hawaiian Islands, barely more than atolls and seamounts, the remnants of volcanoes that once stood tall, but have subsided and eroded over millions of years. Eventually, the chain disappears beneath the ocean as the Emperor seamounts, a string of underwater peaks that mark the hotspot's location tens of millions of years ago. The entire chain is a conveyor belt of creation and decay, a visible record of plate tectonics and the persistence of a deep mantle plume that has fed volcanoes for over 70 million years, patiently adding islands, one lava flow at a time. Obsidian is volcanic glass, formed from rapidly cooled lava. When lava cools so quickly that its atoms don't have time to arrange into crystalline structures, the result is obsidian, a natural glass. Smooth, shiny, and often jet black, obsidian fractures with sharp, conchoidal edges that made it prized by ancient peoples for tool-making. Arrowheads, knife blades, and surgical instruments have all been crafted from this volcanic stone, which can be honed to edges sharper than steel. Obsidian forms most commonly from high silica lava that erupts and cools rapidly, often at a volcano's margins or in the presence of water. The glass is brittle and can shatter easily, but its beauty and utility have made it a valuable trade material throughout human history. Different types of obsidian contain varying amounts of minerals and gases, creating colors from deep black to mahogany, rainbow, or snowflake patterns where crystals began to form. Geologists use obsidian flows to study ancient eruptions, and archaeologists trace its distribution to understand trade networks and cultural connections spanning continents. In obsidian, fire becomes frozen clarity, a stone that holds light and edge in equal measure. Pumice is volcanic rock so light it floats on water. Pumice forms when lava saturated with gas cools rapidly, trapping countless tiny bubbles within the rock. The result is a stone so porous and lightweight that it floats, a paradox of rock and air. Massive eruptions can produce vast rafts of pumice that drift across the ocean for thousands of miles, carrying organisms and even altering shipping routes. The 1883 eruption of Krakatoa created pumice fields that floated in the Indian Ocean for months, some pieces eventually washing ashore as far away as Africa. On land, pumice deposits blanket volcanic regions, forming soft, gravelly plains that crunch underfoot. The stone has practical uses too. Its abrasive texture makes it ideal for polishing and cleaning, and ground pumice is added to soaps, cosmetics, and even toothpaste. In construction, lightweight pumice concrete offers insulation and reduced weight. The stone's porosity also makes it useful in horticulture, improving soil drainage and aeration. Pumice is a reminder that volcanic materials are not all dense and heavy. Some are airy and light, shaped by the gases that drove the eruption itself. Lahars are destructive volcanic mudflows. When volcanic ash and debris mix with water from melting ice, heavy rain, or a crater lake, the result is a lahar, a fast-moving mudflow with the consistency of wet concrete. Lahars can travel at speeds exceeding 50 kilometers per hour, following river valleys and burying everything in their path beneath layers of mud and rock. They are one of the most persistent volcanic hazards, capable of occurring long after an eruption has ceased if heavy rains remobilize loose ash. The 1985 eruption of Nevado del Ruiz in Colombia produced a relatively small eruption, but melted glaciers on the summit, creating lahars that swept down river valleys and buried the town of Armero, killing more than 23,000 people. Lahars can travel for hundreds of kilometers, far beyond the reach of lava or pyroclastic flows, threatening communities that may feel safe from direct volcanic activity. Scientists monitor volcanic regions for lahar risk, constructing channels and barriers to divert flows away from populated areas. Still, the power and speed of these mudflows make them difficult to control, a reminder that waters and earth, combined with volcanic material, create dangers as lethal as fire. Submarine volcanoes can trigger tsunamis. When volcanoes erupt beneath the ocean, the sudden displacement of water can generate tsunamis, waves that race across the sea at hundreds of kilometers per hour. These waves, barely noticeable in deep water, grow to devastating heights as they approach shore, flooding coastlines and causing widespread destruction. The 1883 eruption of Krakatoa triggered tsunamis that killed tens of thousands of people around the Sunda Strait, with waves reaching over 40 meters high in some locations. More recently, the 2022 eruption of Hunga Tonga Hunga Ha'apai in the Pacific produced a tsunami felt around the world, demonstrating that even remote submarine eruptions can have far-reaching impacts. The mechanisms are complex. Collapse of volcanic flanks, entry of pyroclastic flows into the sea, and sudden caldera formation can all displace massive volumes of water. Scientists use seismic networks and ocean sensors to detect submarine eruptions and issue warnings, but the speed and unpredictability of volcanic tsunamis make them especially dangerous. They remind us that the ocean floor is as geologically active as the continents, with hundreds of submarine volcanoes quietly building, erupting, and reshaping the seafloor. Pahoho and AA are two types of lava with different textures. Lava can solidify into different forms depending on its composition, temperature, and rate of flow. Pahoho, a Hawaiian word, describes lava with a smooth, ropey surface. Formed when thin, fluid lava cools slowly while still moving, creating folds and swirls like frozen taffy. Walking on hardened pahoho feels like traversing a glossy, undulating landscape, deceptively smooth but uneven underfoot. By contrast, is rough, jagged, and clinkery, formed when thicker lava moves more slowly and breaks apart as it cools, creating a surface of sharp, loose fragments. Walking on AA is difficult and painful, the broken rock shifting and cutting with every step. Both types can form from the same eruption as lava cools and changes consistency. Pahoho often transitions to AA as it loses heat and becomes more viscous. These textures, though simple to distinguish, reveal much about the conditions of an eruption, the temperature of the lava, the slope it traveled, the gases it contained. They are the vocabulary of volcanic landscapes, written in stone that tells the story of how it flowed and froze. Volcanic gases include water vapor, carbon dioxide, and sulfur dioxide. When magma rises toward the surface, dissolved gases escape in a process called degassing. The most abundant volcanic gas is water vapor, often comprising more than 90% of emissions. Carbon dioxide, sulfur dioxide, hydrogen sulfide, and smaller amounts of other gases make up the rest. These gases can be deadly. Carbon dioxide is heavier than air and can accumulate in low-lying areas, suffocating anyone who enters. In 1986, a sudden release of carbon dioxide from Lake Nyos in Cameroon, a volcanic crater lake, killed over 1,700 people and thousands of animals in nearby valleys. Sulfur dioxide reacts with atmospheric moisture to form acid rain, damaging vegetation and ecosystems downwind of active volcanoes. Hydrogen sulfide smells like rotten eggs and is toxic at high concentrations. Yet volcanic gases also play essential roles in Earth's processes. Over billions of years, volcanic outgassing has contributed to the formation of the atmosphere and oceans, releasing water and carbon dioxide locked in the planet's interior. Even today, volcanoes cycle elements between the deep Earth and the surface, maintaining the chemical balance that supports life. Fumaroles are vents that release volcanic gases and steam. In volcanic regions, the ground is often punctuated by fumaroles, openings through which gases and steam escape continuously. These vents can be found on active volcanoes, in caldera floors, and in areas of geothermal activity. The gases emerge hot, sometimes exceeding 100 degrees Celsius, and the surrounding rock is often stained yellow and orange by sulfur deposits. Walking through a fumarole field feels otherworldly. The ground warm underfoot, the air thick with the smell of sulfur, steam rising in plumes that shift and swirl with the wind. Fumaroles indicate that magma is present below, heating groundwater and driving gases to the surface. They can persist for decades or even centuries, slowly depositing minerals around their vents and creating delicate formations of sulfur crystals and other precipitates. Scientists monitor fumaroles for changes in temperature and gas composition, which can signal rising magma and impending eruptions. In some places, fumaroles are harnessed for geothermal energy or used as natural saunas. They are windows into the Earth's heated interior, reminders that even when a volcano appears quiet, deep processes continue unseen. Mud volcanoes erupt mud instead of lava. Not all volcanoes expel molten rock. Mud volcanoes, found in regions of sedimentary rock and natural gas, erupt mixtures of mud, water, and gases instead. These features form when pressurized gas, often methane, forces its way upward through soft sediments, carrying mud to the surface. The eruptions are usually gentle, producing slow oozes of thick mud that build low cones, though occasionally more violent bursts occur. Azerbaijan is famous for its mud volcanoes, some of which have been active for centuries, bubbling and gurgling in landscapes that feel both barren and alive. Mud volcanoes are not directly related to magma, but share the same principle of subsurface pressure, finding release at the surface. The mud is often cool, rich in minerals, and sometimes used in cosmetic treatments for its supposed therapeutic properties. Though they lack the drama of true volcanic eruptions, mud volcanoes are geological curiosities, blurring the line between solid earth and fluid, between the stillness of rock and the motion of gases seeking escape. Time. Tense. Iceland is one of the most volcanically active places on Earth. Sitting astride the mid-Atlantic ridge, Iceland is a land of fire and ice, where the North American and Eurasian tectonic plates pull apart, allowing magma to rise and create one of the planet's most dynamic volcanic landscapes. The island is dotted with active volcanoes, geothermal fields and lava plains. Eruptions are frequent, sometimes occurring every few years, adding new land and reshaping the terrain. The 2010 eruption of geological, though relatively small, produced an ash cloud that disrupted air travel across Europe for weeks, demonstrating how even modest eruptions can have global impacts. Iceland's volcanic activity is also a source of renewable energy, with geothermal plants providing electricity and heating for much of the population. The landscape itself is a testament to volcanic power. Black sand beaches, columnar basalt formations, steaming hot springs and vast lava fields that stretch to the horizon. Living in Iceland means coexisting with volcanic hazards, but it also means access to abundant energy and landscapes of stark, surreal beauty that draw visitors from around the world. Yellowstone is a supervolcano with the potential for catastrophic eruptions. Beneath Yellowstone National Park lies one of the world's largest volcanic systems, a supervolcano capable of eruptions so massive they could alter global climate and bury vast regions in ash. The Yellowstone caldera, formed by eruptions 640,000 years ago, spans about 55 by 72 kilometers, a testament to the immense power concentrated beneath the park. Geothermal features like Old Faithful and the park's colorful hot springs are surface expressions of the heat below. Yellowstone has erupted 3 times in the past 2 million years, each time producing hundreds or thousands of cubic kilometers of ash and lava. If it were to erupt again, the effects would be catastrophic, with ashfall affecting much of North America and climate impacts felt worldwide. However, scientists emphasize that such eruptions are extremely rare, and current monitoring shows no signs of an imminent event. The volcano is more likely to produce smaller eruptions or lava flows. Yellowstone serves as a reminder of the planet's capacity for truly large-scale volcanic events, forces that dwarf even the most powerful historical eruptions and shape the Earth on continental scales. Pillow lava forms when lava erupts underwater. When molten rock meets the cold embrace of the ocean, it cools so rapidly that it forms rounded, pillow-shaped masses. These pillow lavas are the most common volcanic rock on Earth, covering vast stretches of the ocean floor, where mid-ocean ridges generate new crust. As lava oozes from a fissure underwater, its outer surface solidifies almost instantly, forming a glassy skin. Pressure from the still molten interior causes the pillow to bulge and break, and a new pillow begins to form, piling atop the last. The result is a jumbled stack of smooth, rounded stones, each preserving a record of the moment it froze. Pillow lavas can also form in lakes, or when lava flows reach the sea. Divers exploring these formations find them hauntingly beautiful, smooth and organic looking, like stone loaves stacked in silent bakeries beneath the waves. Geologists study pillow structures to understand ancient environments, as their presence in rock formations on land indicates that those areas were once underwater, evidence of seas that have long since vanished or risen elsewhere. Volcanic islands can form entire archipelagos over millions of years. As tectonic plates drift over stationary hotspots, they leave behind chains of volcanic islands, each recording a moment in the plate's journey. The Hawaiian Emperor chain is perhaps the best known, but similar formations exist around the globe. The Galapagos Islands, for instance, straddle a hotspot near the equator, with the youngest islands to the west still actively volcanic, and the older islands to the east slowly eroding into the sea. These archipelagos are natural laboratories for studying evolution and ecology. Isolated from continents, they host unique species found nowhere else, organisms that evolved in the absence of predators or competitors from larger landmasses. Each island in a chain can have different ages, climates, and ecosystems, creating diversity within a relatively small area. Over time, islands subside as the oceanic crust cools and sinks, eventually becoming seamounts or atolls. Coral reefs perched atop the drowned peaks of ancient volcanoes. The cycle of birth, growth, and erosion continues endlessly, driven by the inexorable motion of plates and the persistence of deep mantle plumes. Basalt is the most common volcanic rock on Earth. When you think of volcanic rock, you're likely thinking of basalt, a dark, fine-grained stone formed from the rapid cooling of low silica lava. Basalt is the foundation of the ocean floor, the product of countless eruptions along mid-ocean ridges where tectonic plates pull apart. It also forms vast plateaus on land, such as the Deccan Traps in India and the Columbia River basalt group in the United States, remnants of massive flood basalt eruptions that covered thousands of square kilometers in layer upon layer of lava. Basalt is dense and durable, prized as a building material and road aggregate. Its dark color comes from iron and magnesium-rich minerals, giving it a characteristic weight and strength. When basalt cools slowly, it can form distinctive columnar jointing, hexagonal pillars that look like giant stone pencils standing on end, a natural geometry created by contraction as the rock solidifies. Basalt landscapes feel ancient and enduring, their dark stone absorbing sunlight and radiating warmth, a reminder of the fiery origins hidden beneath a surface that seems cold and still. Andesite and rhyolite are other common volcanic rocks. While basalt dominates oceanic environments, andesite and rhyolite are more common in continental volcanic regions. Andesite, named for the Andes Mountains, forms from magma with intermediate silica content, producing rocks lighter in color and weight than basalt. Its composition reflects the melting of oceanic crust as it sinks beneath continents, mixing elements from both sources. Andesite eruptions can be explosive, producing ash and pyroclastic flows alongside lava. Rhyolite, the volcanic equivalent of granite, forms from high silica magma that is thick, sticky, and prone to trapping gases. Eruptions of rhyolite are often highly explosive, creating vast ash deposits and sometimes ignimbrites, sheets of welded volcanic material that cover landscapes in hot, glowing clouds. Rhyolite's light color, often pink or gray, reflects its composition, rich in quartz and feldspar. These rocks tell stories of different magma sources and eruptive styles, from the gentle effusions of basalt to the catastrophic blasts of rhyolite, each a chapter in the Earth's volcanic diversity. Volcanoes help regulate Earth's carbon cycle over geological time. Over millions of years, volcanoes play a crucial role in balancing the planet's carbon budget. They release carbon dioxide stored in the Earth's interior, adding it to the atmosphere, where it can influence climate. At the same time, the weathering of volcanic rock removes carbon dioxide from the air, as rainwater reacts with silicate minerals to form carbonates that eventually wash into the ocean and settle as limestone. This cycle operates on timescales far longer than human lifetimes, yet it has shaped Earth's climate throughout its history. During periods of intense volcanic activity, such as the formation of large igneous provinces, carbon dioxide levels can rise, warming the planet. During quieter periods, weathering outpaces outgassing, and the climate cools. The balance is delicate and slow, but it demonstrates that volcanoes are not merely destructive forces, but essential components of the Earth system, cycling elements between the deep interior and the surface, regulating temperature and maintaining conditions suitable for life. Volcanic eruptions have triggered mass extinctions in Earth's history. Some of the most devastating events in the history of life have been linked to massive volcanic eruptions. The Permian Triassic extinction, the worst mass extinction ever, occurred around 252 million years ago and may have been triggered by the eruption of the Siberian Traps, a flood basalt province that covered millions of square kilometers with lava. The eruptions released enormous amounts of carbon dioxide and sulfur dioxide, warming the planet, acidifying the oceans, and creating conditions hostile to most life forms. More than 90% of marine species and 70% of terrestrial species vanished. The Deccan Traps in India, which erupted around the same time as the asteroid impact that ended the age of dinosaurs, may have contributed to the Cretaceous-Paleogene extinction as well. These events remind us that while individual eruptions are temporary, the cumulative effects of prolonged volcanic activity can alter the planet's climate and ecosystems on a global scale, shaping the course of evolution and the rise and fall of entire lineages. The eruption of Krakatoa in 1883 was heard thousands of kilometers away. On August 27, 1883, the island volcano of Krakatoa in Indonesia exploded with a violence that shattered the island and sent shockwaves around the globe. The sound of the eruption is considered the loudest in recorded history, heard as far as 4,800 kilometers away in Australia and the island of Rodrigues near Mauritius. Closer to the source, the blast ruptured eardrums and shattered windows. The explosion generated tsunamis that killed more than 36,000 people in coastal communities around the Sunda Strait, and ash fell across a vast region, plunging areas into darkness for days. The eruption ejected massive amounts of material into the atmosphere, creating spectacular sunsets around the world for months, as volcanic aerosols scattered light. The island itself was largely destroyed, leaving a deep, underwater caldera. In the decades since, a new volcano, Anak Krakatau, or Child of Krakatoa, has emerged from the sea, rebuilding the volcanic cone in the same location, a reminder that even the most destructive eruptions are merely pauses in an ongoing cycle. Mount St. Helens erupted dramatically in 1980. On May 18, 1980, Mount St. Helens in Washington state erupted in one of the most closely observed and documented volcanic events in history. The eruption was triggered by a massive landslide that removed the northern flank of the mountain, releasing pressure on the magma chamber beneath. The result was a lateral blast that devastated an area of 600 square kilometers, flattening forests and killing 57 people. An ash column rose more than 24 kilometers into the sky, and lahars swept down river valleys, destroying bridges and infrastructure. The eruption transformed the landscape, creating a barren moonscape where lush forests had stood. In the decades since, The area has become a natural laboratory for studying ecological recovery. Plants and animals have gradually returned, colonizing the ash-covered slopes. The mountain itself continues to rebuild, with a new lava dome growing inside the crater. Mount St. Helens serves as a powerful reminder of volcanic hazards in the Pacific Northwest, where several similar peaks, including Mount Rainier and Mount Hood, remain active and closely monitored. Lava tubes are natural tunnels formed by flowing lava. As lava flows downhill, its surface cools and solidifies, while the molten interior continues to move. When the eruption ceases and the lava drains away, it can leave behind a hollow tube, a natural tunnel through the hardened crust. These lava tubes can extend for kilometers, forming complex networks beneath volcanic landscapes. Exploring a lava tube is like stepping into another world, the walls smooth and rippled from the passage of molten rock. The ceiling sometimes hung with delicate formations called lava sickles, frozen drips of once fluid stone. Some lava tubes are large enough to walk or even drive through, and they provide shelter and stable temperatures that make them useful as natural refrigerators or hiding places. On the Big Island of Hawaii, lava tubes are tourist attractions, offering glimpses into the mechanics of flowing lava. They also serve as potential habitats on other planets. Scientists study Earth's lava tubes as analogues for similar features discovered on the Moon and Mars, places where future explorers might find shelter from radiation and temperature extremes. Lava fountains can shoot hundreds of meters into the air. During some eruptions, lava is ejected into the air in spectacular fountains, arcs of molten rock glowing bright orange against the sky. These fountains form when gas-rich magma reaches the surface, and the sudden release of pressure propels lava upward. Fountains can reach heights of several hundred meters, creating curtains of fire that illuminate the night. As the lava arcs through the air, it cools and breaks into fragments, falling back to the ground as spatter or forming cinder cones around the vent. Hawaiian eruptions often feature sustained lava fountains that pulse rhythmically, driven by gas bubbles rising through the magma column. Witnessing a lava fountain is both beautiful and humbling. It's a visceral reminder of the energy stored beneath the Earth's surface. The heat is intense, even at a distance, and the roar of escaping gases and the hiss of cooling lava create a symphony of sound that drowns out everything else. Lava fountains are ephemeral, lasting minutes to hours, but they leave lasting impressions on those who see them and lasting deposits on the landscape they reshape. Volcanoes create fertile soils that support agriculture. Despite their destructive power, volcanoes are also creators of life. Volcanic ash and weathered lava produce some of the most fertile soils on Earth, rich in minerals like potassium, phosphorus, and calcium that plants need to thrive. Regions near active volcanoes, such as Java, the slopes of Mount Etna, and the Rift Valley of East Africa, support dense populations sustained by abundant crops. The soil's fertility comes from the rapid breakdown of volcanic minerals, a process that releases nutrients more quickly than the weathering of other rock types. This fertility has drawn people to live near volcanoes for millennia, despite the risks. Rice paddies, coffee plantations, vineyards and fields of vegetables blanket volcanic slopes, green and lush, even in the shadow of smoking peaks. The trade-off between danger and prosperity is an ancient one, and many cultures have developed rituals, warning systems, and architectural adaptations to coexist with volcanoes. The same mountains that threaten with fire and ash also provide the foundation for thriving communities, a duality that defines volcanic regions around the world. Some volcanic eruptions produce lightning storms within ash clouds. The collision of ash particles, ice, and rock fragments within a volcanic plume can generate intense electrical charges, resulting in lightning that crackles through the eruption column. These volcanic lightning storms are visually stunning, with bolts arcing between the cloud and the ground, or streaking horizontally through the ash. The phenomenon occurs because particles of different sizes and compositions become electrically charged as they collide. Much like in a thunderstorm, the charges build until the voltage difference is great enough to ionize the air, creating lightning. Researchers study volcanic lightning to understand eruption dynamics, as the intensity and frequency of lightning can reveal details about the amount of ash being ejected and the violence of the eruption. Photographs of volcanic lightning show a dramatic interplay of fire and electricity, nature's raw power on a full display. For observers, the spectacle is unforgettable, a convergence of elemental forces that seems almost mythical in its intensity. Tephra is the term for all solid material ejected by a volcano. Volcanic eruptions expel more than lava. They produce tephra, a collective term for all fragments of rock, ash, and pumice thrown into the air. Tephra ranges in size, from fine ash particles smaller than a millimeter to massive blocks weighing several tons. The size and distribution of tephra depend on the eruption's explosivity and wind patterns. Fine ash can travel thousands of kilometers, blanketing distant regions and disrupting air travel, while larger fragments fall closer to the vent, building cones and covering nearby terrain. Tephra layers preserved in the geological record serve as time markers, allowing scientists to date and correlate events across wide areas. The 79 AD eruption of Vesuvius left distinct tephra layers that archaeologists use to date ruins and study ancient life. Tephra is also studied for its impact on climate, ecosystems, and human health. Inhaling fine ash can damage lungs, and heavy tephra fall can collapse buildings. Yet tephra also contributes to soil formation, adding minerals and nutrients that enrich the land over time. Mount Etna is one of the world's most active volcanoes. Rising above the island of Sicily, Mount Etna has been erupting almost continuously for thousands of years, making it one of the most studied and active volcanoes on Earth. Its eruptions range from gentle lava flows to explosive bursts of ash and gas, and the mountain's summit is constantly changing, with new craters opening and old ones collapsing. Etna's activity is driven by its position above a complex tectonic setting, where the African plate meets the Eurasian plate. Despite its activity, millions of people live on its slopes, drawn by fertile soils and the beauty of the landscape. The volcano is deeply embedded in Sicilian culture, appearing in myths, literature, and art for centuries. Ancient Greeks believed it was the forge of Hephaestus, the god of fire and metalworking. Today, Etna is a tourist destination, with visitors hiking to the summit, exploring lava caves, and tasting wines grown in volcanic soil. The mountain's frequent eruptions serve as reminders that the earth is alive, breathing fire, and reshaping the land with every pulse of magma from below. Volcanic eruptions can create new landmasses. In the dynamic interplay of creation and destruction, volcanic eruptions sometimes add entirely new land to the planet's surface. Surtsey, which emerged off Iceland's coast in 1963, is a famous example. Over several years, repeated eruptions built an island from nothing, a raw expanse of black rock rising from the sea. Scientists watched as life colonized the barren surface, documenting each stage of ecological succession. Other volcanic islands have appeared more recently, some enduring and others eroding away before they could be named. In Hawaii, lava from Kilauea has added hundreds of acres to the Big Island's coastline, extending the land into the ocean. These additions are fragile at first, subject to wave action and collapse. But over time, they solidify and become permanent features. The process of land creation is slow but relentless, each flow adding a layer, each eruption expanding the island's footprint. Volcanic land building is a reminder that the Earth's geography is not fixed. Coastlines shift, islands appear, and the map of the world is rewritten, one eruption at a time. Mauna Loa is the largest volcano on Earth by volume. Rising from the floor of the Pacific Ocean, Mauna Loa is a giant among volcanoes. Though its summit stands 4,169 meters above sea level, its true height from base to peak is over 9,000 meters. Taller than Mount Everest, the volcano's volume is staggering, approximately 75,000 cubic kilometers, making it the largest active volcano on the planet. Mauna Loa is a shield volcano, built from countless eruptions of fluid basaltic lava that spread across vast areas, layer upon layer, over hundreds of thousands of years. It erupts frequently, with the most recent eruption in 2022, sending lava flows down its flanks. The volcano's massive size and gentle slopes make it appear almost benign, but its eruptions can produce enormous volumes of lava, threatening communities and infrastructure on the Big Island. Scientists monitor Mauna Loa closely, using seismic networks, GPS, and gas sensors to detect signs of unrest. The volcano is a living testament to the power of hotspot volcanism, a mountain that continues to grow, fed by a deep mantle plume that has shaped the Hawaiian Islands for millions of years. Volcanic winter can occur after large eruptions. When a massive volcanic eruption injects sulfur dioxide and ash high into the stratosphere, the resulting aerosol cloud can reflect sunlight away from Earth, cooling the planet and disrupting weather patterns. This phenomenon, known as volcanic winter, can last for years, leading to crop failures, famines, and social upheaval. The eruption of Mount Tambora in 1815 caused the year without a summer in 1816, with snowfall in June and widespread agricultural collapse. The effects rippled through societies, contributing to food shortages and even inspiring Mary Shelley to write Frankenstein during a gloomy summer spent indoors. Volcanic winter demonstrates the interconnectedness of Earth systems, how an eruption on a remote island can alter global climate and affect millions of lives. Scientists study past volcanic winters to understand their mechanisms and predict the potential impacts of future large eruptions. The risk is real but rare, a reminder that while volcanic eruptions are local events, their consequences can be felt around the world, shaping human history in unexpected ways. The Deccan Traps are remnants of massive ancient eruptions. In west-central India, a vast plateau of layered basalt covers an area of more than 500,000 square kilometers, the remnants of one of Earth's most massive volcanic events. The Deccan Traps formed around 66 million years ago, during a period of intense flood basalt eruptions that lasted for hundreds of thousands of years. Each eruption added a layer of lava, and over time, these layers accumulated to thicknesses exceeding 2 kilometers in some places. The eruptions released enormous amounts of volcanic gases, contributing to climate change and possibly playing a role in the mass extinction that ended the age of dinosaurs. The timing of the Deccan eruptions coincides closely with the asteroid impact at Chicxulub, and scientists debate the relative contributions of each event to the extinction. Today, the Deccan Traps are a landscape of stepped plateaus and rugged terrain, the eroded edges of ancient lava flows. They serve as a window into Earth's violent past, evidence of volcanic activity on a scale almost unimaginable today. Volcanic vents can emit blue flames from burning sulfur. In certain volcanic regions, particularly in Indonesia, sulfur-rich gases emerge from fumaroles and ignite upon contact with the air, producing eerie blue flames. The Ijen volcano in East Java is famous for this phenomenon. Miners extract sulfur from the crater, working in harsh conditions amid toxic gases and searing heat. At night, the blue flames glow against the dark, an otherworldly sight that draws photographers and adventurers. The flames result from the combustion of sulfuric gases at temperatures exceeding 600 degrees Celsius. Sulfur also condenses around the vents, forming bright yellow deposits that miners collect and carry down the mountain in baskets. The work is dangerous and poorly paid, a testament to the extremes humans will endure to extract resources from volcanic environments. The blue flames of Ijen are beautiful but hazardous, a reminder that volcanic landscapes are places of both wonder and peril, where the Earth's chemistry is on vivid, burning display. Some volcanoes have crater lakes that are highly acidic. Crater lakes form when volcanic craters fill with water from rainfall, melting snow, or groundwater. In some cases, these lakes are fed by volcanic gases and heat, creating bodies of water that are highly acidic, sometimes with pH levels below 1, rivaling battery acid. The acidity comes from dissolved sulfur dioxide, hydrochloric acid, and other volcanic gases. These lakes can be strikingly colored, ranging from turquoise to deep green or brown, depending on the dissolved minerals and microbial life. Kawah Ijen in Indonesia hosts one such lake, a brilliant turquoise pool that hides its lethal chemistry beneath a beautiful surface. Crater lakes can pose hazards beyond their acidity. Sudden releases of carbon dioxide, known as limnic eruptions, can suffocate nearby populations. Volcanic heat can cause lakes to boil or overflow, triggering lahars. Despite the dangers, crater lakes are fascinating natural laboratories for studying extremophile organisms and volcanic processes. They are places where beauty and danger coexist, where the Earth's heat and chemistry create conditions found almost nowhere else. Volcanic eruptions can be predicted with varying degrees of accuracy. Modern volcano monitoring combines seismology, gas analysis, ground deformation measurements, and thermal imaging to detect signs of impending eruptions. Increasing earthquake activity, swelling of the volcano's flanks, changes in gas emissions, and rising temperatures often precede eruptions, giving scientists clues about what's happening beneath the surface. In some cases, eruptions can be predicted days or weeks in advance, allowing for evacuations that save countless lives. The 1991 eruption of Mount Pinatubo in the Philippines was successfully forecasted, and timely evacuations saved tens of thousands. However, not all eruptions give clear warning signs, and some occur with little or no precursor activity. The science of volcano prediction is improving, but it remains imperfect. a humbling reminder of the limits of our understanding. False alarms can erode public trust, while missed warnings can be catastrophic. Scientists balance these risks carefully, communicating uncertainties and probabilities, while working to refine their tools and models, always striving to better protect the communities that live in the shadows of active volcanoes. Iceland's volcanic activity is increasing due to tectonic spreading. Iceland sits atop the mid-Atlantic ridge, where the North American and Eurasian plates are pulling apart at a rate of about 2 centimeters per year. This tectonic spreading creates conditions for frequent volcanic activity as magma rises to fill the gap left by the separating plates. Recent years have seen increased volcanic unrest in Iceland, with eruptions on the Reykjanes Peninsula, region that had been quiet for centuries. The eruptions are characterized by fish events, long cracks in the ground that spew lava in dramatic curtains of fire. These eruptions are relatively gentle compared to explosive stratovolcanoes, but they still pose risks to nearby towns and infrastructure. Iceland's unique position makes it a natural laboratory for studying rift volcanism, and scientists from around the world come to observe and learn. The increase in activity is likely part of a long-term cycle, a reminder that volcanic systems operate on timescales far longer than human lifetimes, waking and sleeping in rhythms dictated by the movement of the Earth's crust. Some volcanic rocks contain crystals that form deep underground. Within volcanic rocks, geologists often find crystals that tell stories of the magma's journey from deep within the Earth. These crystals, such as olivine, pyroxene, and feldspar, form slowly as magma cools at depth, growing layer by layer in the heat and pressure of the magma chamber. When the magma finally erupts, it carries these crystals to the surface, embedding them in rapidly cooled lava or ash. By studying the crystals, scientists can infer the temperature, pressure, and composition of the magma at different depths, reconstructing the volcano's plumbing system. Some crystals show complex zoning, layers of different compositions that record changes in the magma chamber over time, such as injections of fresh magma or mixing of different sources. Others contain tiny pockets of trapped magma called melt inclusions, which preserve a snapshot of the magma's chemistry before eruption. These crystals are time capsules, carrying information from realms we can never visit, revealing the hidden processes that feed volcanoes and drive eruptions. Resurgent domes form when magma pushes up the floor of a caldera. After a caldera forming eruption empties a magma chamber and causes the surface to collapse. New magma can rise into the void, pushing the caldera floor upward in a feature called a resurgent dome. These domes can grow over thousands of years, sometimes forming islands within crater lakes or uplifted plateaus within larger depressions. The Yellowstone caldera contains 2 resurgent domes, the Sour Creek and Mallard Lake domes, which have risen several hundred meters since the last major eruption. Resurgent domes are evidence that volcanic systems do not die after a major eruption, but can rebuild, accumulating magma and potentially setting the stage for future activity. Monitoring these domes helps scientists understand the rate at which magma is recharging beneath a volcano and the likelihood of future eruptions. Resurgent calderas are among the most closely watched volcanic features, as they represent some of the planet's largest and most powerful volcanic systems, capable of eruptions that can reshape continents and alter global climate. Volcanic bombs are large blobs of lava ejected during eruptions. During explosive eruptions, molten lava can be thrown high into the air, cooling and solidifying as it arcs through the sky. These projectiles, called volcanic bombs, can range in size from a few centimeters to several meters across. The largest bombs weigh many tons and can be hurled kilometers from the vent. As they fly, they often take on aerodynamic shapes, spinning and stretching into forms that resemble footballs, teardrops, or twisted ribbons. Some bombs are hollow, filled with gas bubbles, while others are dense and solid. Landing with tremendous force, bombs can crush structures, ignite fires, and create impact craters in the ground. Despite their danger, volcanic bombs are prized by geologists and collectors for their dramatic shapes and the insights they provide into eruption dynamics. Studying the distribution and characteristics of bombs helps reconstruct the violence and direction of past eruptions, adding another piece to the puzzle of understanding volcanic behavior. Some volcanoes erupt at regular intervals like clockwork. While most volcanoes erupt unpredictably, a few have shown remarkable regularity. Old Faithful in Yellowstone is a geyser, not a volcano, but it demonstrates the principle of periodic eruptions driven by underground heat. Some true volcanoes, particularly those with simple magma supply systems, erupt at roughly regular intervals. Stromboli in Italy has been erupting almost continuously for centuries, with small explosions occurring every few minutes to hours, earning it the nickname Lighthouse of the Mediterranean. The regularity comes from a consistent magma supply and gas release mechanism. However, even these volcanoes can break their patterns, experiencing larger or smaller eruptions that disrupt the cycle. Predicting eruptions based on past patterns is useful, but not foolproof, as volcanic systems are complex and influenced by many variables. Still, the existence of periodic eruptions offers hope that with careful monitoring and study, scientists can improve their ability to forecast volcanic activity, giving communities more time to prepare and respond to the restless mountains in their midst. Volcanic activity on other planets and moons reveals diverse processes. Earth is not the only world with volcanoes. Mars hosts Olympus Mons, the largest volcano in the solar system, a shield volcano so vast it dwarfs any on Earth. Venus is covered with volcanic features, its surface shaped by lava flows and massive shield volcanoes. Io, a moon of Jupiter, is the most volcanically active body known, with hundreds of active volcanoes spewing sulfur and silicate lava into space, driven by tidal heating from Jupiter's immense gravity. Even icy moons like Enceladus and Europa exhibit cryovolcanism, erupting water, ammonia, and other volatiles instead of molten rock. Studying extraterrestrial volcanism expands our understanding of planetary processes, showing that volcanism is a common feature of rocky and icy bodies throughout the solar system. These distant volcanoes remind us that the forces shaping Earth are not unique, but part of a broader story of planetary evolution, a narrative written in lava and ice across the cosmos. The study of volcanoes is called volcanology. Volcanology is the scientific discipline dedicated to understanding volcanoes, their eruptions, and their impacts. Volcanologists study a wide range of phenomena, from the chemistry of magma to the mechanics of eruptions, the formation of volcanic rocks, and the hazards posed to human populations. The field combines geology, chemistry, physics, and even biology as researchers explore how life adapts to volcanic environments. Fieldwork often involves traveling to remote and dangerous locations, sampling gases from fumaroles, mapping lava flows, and installing monitoring equipment on active Volcanoes. Volcanologists also work in laboratories, analyzing rock samples, modeling eruption processes, and interpreting seismic data. The goal is to improve our ability to predict eruptions, mitigate hazards, and understand the role of volcanoes in Earth's system. Advances in technology, such as satellite monitoring and computer modeling, have revolutionized the field, allowing scientists to observe and analyze volcanoes in ways that were impossible just a few decades ago. Volcanology is a dynamic and evolving discipline, driven by curiosity and the urgent need to protect communities living near active volcanoes. Volcanic ash can disrupt air travel for weeks. In 2010, the eruption of Geologically in Iceland produced an ash cloud that drifted over Europe, grounding tens of thousands of flights and stranding millions of passengers. The disruption lasted for weeks, costing airlines billions of dollars. The ash posed a serious hazard to aircraft because volcanic particles can melt inside jet engines, causing them to fail. Even thin ash clouds at high altitudes are dangerous, and aviation authorities err on the side of caution, closing airspace until the hazard has passed. Volcanic ash is also a threat to navigation systems and can damage aircraft surfaces. The 2010 event highlighted the vulnerability of modern air travel to volcanic eruptions, even relatively small ones. Since then, improved monitoring and modeling have helped authorities better predict ash dispersion and minimize disruptions. However, the risk remains, particularly in regions with active volcanoes beneath major flight paths. Volcanic ash reminds us that natural hazards do not respect borders, and that the impacts of eruptions can ripple through global systems in unexpected ways. Mount Fuji is a sacred and culturally significant volcano in Japan. Rising 3,676 meters above sea level, Mount Fuji is Japan's tallest peak and one of its most iconic symbols. The symmetrical stratovolcano has inspired artists, poets, and pilgrims for centuries, appearing in countless works of art, including Hokusai's famous woodblock prints. Fuji is considered sacred in Shinto and Buddhist traditions, and climbing the mountain is a spiritual journey for many. Despite its cultural significance, Mount Fuji is an active volcano, last erupting in 1707. That eruption, known as the Hoi eruption, covered Edo, modern Tokyo, in ash and caused widespread disruption. Today, scientists monitor Fuji closely, aware that a future eruption could affect millions of people living in the surrounding region. The mountain's beauty and tranquility belie the molten forces beneath, a duality that resonates deeply in Japanese culture. Mount Fuji embodies the coexistence of humanity and nature, reverence and risk, serving as a reminder that even the most beloved landscapes are shaped by forces beyond our control. Rootless cones are formed by lava interacting with water or ice. In Iceland and other volcanic regions, small cinder cones called rootless cones or pseudocraters dot the landscape. Unlike typical volcanic cones, these features have no connection to a magma chamber. Instead, they form when lava flows over wet ground, marshes or ice, causing the water to flash into steam. The explosive expansion of steam blasts through the lava, ejecting fragments and creating small craters surrounded by rims of debris. Rootless cones are typically only a few meters to tens of meters tall, far smaller than true volcanic cones. They cluster in groups where lava flows encountered ponds or ice sheets, creating fields of dozens or even hundreds of small craters. These features offer insights into the conditions present during ancient eruptions, such as the presence of lakes or glaciers. They also demonstrate the diverse ways that lava can interact with its environment, creating a variety of landforms beyond the simple picture of molten rock flowing downhill. Volcanic eruptions can create their own weather systems. The heat and moisture released during a volcanic eruption can generate localized weather phenomena, including thunderstorms, heavy rain, and even tornadoes. The eruption column acts like a massive heat source, driving powerful convection currents that draw in surrounding air and moisture. As the column rises, water vapor condenses, forming clouds and precipitation. These volcanic storms can produce lightning, heavy rain, and strong winds, adding to the hazards faced by nearby communities. In some cases, volcanic eruptions have triggered lahars by producing heavy rain that mobilizes ash and debris on the volcano slopes. The interaction between eruptions and weather is complex and not fully understood, but it highlights the interconnectedness of Earth's systems. A volcano is not just a geological feature, but a dynamic force that influences the atmosphere, hydrosphere, and biosphere, creating feedbacks that ripple through the environment in ways both subtle and dramatic. Columnar jointing creates hexagonal rock formations. When thick lava flows cool, slowly, and evenly, they can develop a striking pattern called columnar jointing, where the rock fractures into vertical columns, often hexagonal in cross-section. This natural geometry forms because as lava cools, it contracts, and the most efficient way to relieve the stress is to crack into polygonal shapes. The columns can be remarkably uniform, resembling stacks of stone pencils or organ pipes. Famous examples include the Giant's Causeway in Northern Ireland and Devil's Postpile in California. The columns can be several meters tall and perfectly straight, or they can curve and twist, depending on the cooling rate and the flow's geometry. Columnar jointing is not unique to lava. It can also form in thick ash flows and other volcanic deposits. The formations are a testament to the orderly processes that can emerge from the chaos of an eruption, a reminder that nature often finds elegant solutions to the physical stresses imposed by heat, pressure, and time. Volcanic soils are among the most fertile in the world. The weathering of volcanic rock releases nutrients that make volcanic soils exceptionally fertile, supporting dense vegetation and productive agriculture. Minerals like potassium, phosphorus, and magnesium, essential for plant growth, are abundant in volcanic ash and lava. Over time, as these materials break down, they create soils that are rich, dark, and highly productive. Regions like Java, the slopes of Mount Etna, and parts of Central America owe their agricultural abundance to volcanic soils. These soils can support multiple harvests per year and sustain large populations. However, the fertility is not permanent. Without proper management, volcanic soils can erode or become depleted. Yet the same volcanoes that created the soils can renew them, adding fresh layers of ash and minerals with each eruption. This cycle of destruction and renewal has shaped human settlement patterns for millennia, drawing people to live near volcanoes despite the risks, trading danger for the promise of abundance. Lava lakes are rare and mesmerizing features. A lava lake is a pool of molten lava contained within a volcanic crater or vent, a rare phenomenon found at only a handful of volcanoes worldwide. Kilauea in Hawaii and Erta-Ale in Ethiopia are among the few that host persistent lava lakes. The surface of a lava lake is constantly in motion, roiling and churning as gases escape, and fresh magma wells up from below. The crust that forms on the surface cracks and shifts, revealing glimpses of the incandescent liquid beneath. Lava lakes offer scientists a unique opportunity to study magma behavior in real time, observing processes that normally occur deep underground. Researchers use thermal cameras, drones, and seismic monitoring to track changes in the lake's level, temperature, and activity, seeking clues about the volcano's deeper plumbing. For visitors, witnessing a lava lake is an unforgettable experience, standing at the edge of a crater and gazing into the glowing heart of the earth, feeling the heat on your skin and hearing the hiss and rumble of molten rock just meters away. Volcanic eruptions have shaped human history and mythology. Throughout history, volcanic eruptions have left deep marks on human cultures, inspiring myths, shaping migrations, and altering the course of civilizations. The eruption of Thera, Santorini, around 1600 BC, may have contributed to the collapse of the Minoan civilization and inspired the legend of Atlantis. The eruption of Vesuvius in 79 AD preserved Pompeii and Herculaneum, offering modern archaeologists a snapshot of Roman life. Volcanic events have been woven into mythologies around the world, from Pele in Hawaii to the Maori stories of New Zealand's volcanic plateau. Eruptions have forced populations to flee, destroyed cities, and altered trade routes. They have also provided resources, from fertile soils to obsidian for tools and sulfur for industry. The relationship between humans and volcanoes is ancient and complex, marked by both reverence and fear, adaptation and loss. Volcanoes remind us that we are part of a dynamic planet, subject to forces far greater than ourselves, forces that have shaped not only the land we live on, but also the stories we tell and the ways we understand our place in the world. Volcanic activity continues beneath the surface, even between eruptions. A volcano does not go silent when it stops erupting. Beneath the surface, magma continues to move, gases percolate through cracks, and heat radiates into surrounding rock. Seismometers detect thousands of tiny earthquakes each year at many volcanoes, evidence of magma shifting and rock cracking under stress. Ground deformation measurements reveal that some volcanoes swell and subside over months or years as magma chambers fill and drain. Fumaroles and hot springs release volcanic gases continuously, providing clues about the activity below. This ongoing unrest means that volcanoes are never truly dormant, only resting between episodes of surface activity. Monitoring this background activity is crucial for detecting changes that might signal an impending eruption. Scientists use networks of instruments, from seismometers and GPS stations to gas sensors and satellite radar, to keep watch over restless peaks. The data they collect build a picture of the volcano's hidden life, the slow accumulation of pressure, the migration of fluids, and the deep processes that will one day bring magma back to the surface. The Pacific Ring of Fire is also known as the Circum-Pacific Belt. Encircling the Pacific Ocean, the Ring of Fire is a nearly continuous chain of volcanic arcs and oceanic trenches, home to most of the world's earthquakes and eruptions. This belt of fire and movement is the result of tectonic plates converging, diverging, and sliding past one another, creating a dynamic boundary where the Earth's internal heat finds release. From New Zealand to Japan, from Alaska to Chile, the Ring of Fire shapes landscapes and lives, a reminder that our planet is restless. The peoples who live within this zone have developed rich traditions of resilience, building flexible homes, creating early warning systems, and weaving volcanic events into their cultural narratives. The Ring of Fire is not a curse, but a testament to the planet's vitality, a zone where creation and destruction are intertwined, where the forces that built mountains and islands continue their work, indifferent to human timescales, patient beyond measure. Volcanic gases can be toxic and deadly to humans and animals. Volcanoes release a cocktail of gases, some of which are deadly in high concentrations. Carbon dioxide, being heavier than air, can accumulate in depressions, displacing oxygen and causing asphyxiation. Sulfur dioxide irritates the respiratory system and can combine with moisture to form acid rain. Hydrogen sulfide, which smells like rotten eggs at low concentrations, is toxic and can cause respiratory failure at higher levels. Fluorine gases can poison vegetation and water supplies, affecting livestock and agriculture. The dangers are not limited to active eruptions. Even quiescent volcanoes can release gases that pose risks to people and animals living nearby. In volcanic regions, gas monitoring is an essential part of hazard assessment. Scientists measure concentrations and track changes over time, looking for signs of increasing activity. For communities living near volcanoes, awareness of gas hazards is crucial. Simple measures, like avoiding low-lying areas after an eruption or monitoring air quality, can save lives. A reminder that volcanic threats extend beyond the visible drama of lava and ash. Volcanoes play a role in the formation of mineral deposits. The heat and fluids associated with volcanic activity concentrate valuable minerals in ways that make them economically viable to extract. Hydrothermal systems, where hot water circulates through rock, can deposit gold, silver, copper, and other metals in veins and ore bodies. Volcanic regions are often rich in minerals like sulfur, pumice, and perlite, used in industry and construction. Some of the world's largest copper and gold deposits are associated with ancient volcanic systems. The same processes that build mountains also create the resources humans depend on. Geologists study volcanoes not only to understand eruptions, but also to locate mineral wealth, using clues from volcanic rocks and geothermal activity to find hidden deposits. The relationship between volcanoes and minerals is a reminder that Earth's internal processes, violent and destructive as they can be, also generate the resources that support modern civilization, from the metals in our electronics to the materials that build our homes. Volcanoes can create natural fireworks displays at night. Watching a volcano erupt at night is a spectacle of light and motion, a natural fireworks display that rivals anything created by human hands. Lava fountains glow orange and red against the darkness, arcing into the sky and painting the clouds with reflected light. Lava flows creep down slopes, rivers of fire that illuminate the landscape in surreal hues. Explosions send incandescent fragments spiraling upward, trailing sparks and ash. Lightning crackles through eruption columns, adding electric brilliance to the scene. The roar of escaping gases, the hiss of cooling lava, and the deep rumble of the earth itself create a symphony of sound that accompanies the visual feast. For those who witness such events, the experience is transformative, a reminder of the raw power and beauty of the natural world. Volcanic eruptions at night strip away the ordinary and reveal the extraordinary, offering a glimpse of the planet's fiery heart, a vision that lingers long after the glow has faded and the ash has settled. Beneath every ridge and meadow, deep under rock and stone, the earth continues its patient work. Volcanoes do not rush. They gather strength in rhythms older than memory, their fires born from pressures that build slowly in the dark. What we see as a volcano is only the surface of something vaster, the visible expression of forces that shaped continents, carved ocean basins, and breathed the first atmospheres into being. As you rest now, imagine those hidden chambers of heat and stone, the slow rise of magma through fractures in the crust, the whisper of gases escaping toward the light. Even the stillest peak carries motion within it, a heartbeat measured in centuries, a breath that spans millennia. Volcanoes remind us that creation is not separate from destruction, that what crumbles becomes soil, what burns becomes new land. They show that strength is not rigidity, but the ability to transform, to release pressure, to reshape and renew. Every fragment of ash is a seed of fertility. Every lava flow the foundation of future forests. Let that thought carry you now. The world beneath your feet is alive, vast, and endlessly creative. It moves slowly enough for you to rest within it, safely held in the warmth of deep time. If you enjoyed this quiet journey, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let your eyes grow heavy, and let the glow of distant peaks warm your thoughts as you drift into sleep. Good night.